Hello, my name is Mauro Marchetti and I am the CEO of Anteverta-mw. Anteverta is a part of Maury Microwave Corporation and we specialized on active load pool measurement systems and large signal measurements in general. In this presentation, I will give an overview of active load pool measurement techniques with an emphasis on wideband load impedance control for modulated signal measurements. So this is the outline of this presentation. After a short introduction, I will give an overview of active load pool techniques. Afterwards, I will discuss the challenges related to performing load pool measurements with modulated signals and present the techniques that allow wideband impedance control. Furthermore, I will discuss some additional requirements for linearity characterization, such as baseband impedance control, and then finally draw some conclusions. As we all know, today's race for efficiency in wireless transceivers requires power amplifiers that are more and more efficient. Higher amplifier classes employ the devices in a highly nonlinear region and make use of harmonic terminations to achieve higher efficiency at the expense of linearity. Now, to support nonlinear PA design, one needs to have either accurate nonlinear device models, which aren't always easy to come by, or large signal measurement capabilities such as load pool. Load pool is a very widely established tool to support the design and the model extraction and validation of nonlinear transistors. As you've probably already seen from the previous presentation in this short course, a load pool measurement system is capable of tuning the source and load impedance at fundamental and often also at the harmonic frequencies, while measuring all the performance parameters of the transistor, such as power, efficiency, linearity, RF voltage and current waveforms, and so on. Our modern load pool systems can support not only CW and post-CW signals, but also two-tone and complex modulated signals, and measure quantities such as ACPR, EVM, and bit error rate. There are different techniques to perform load pool. The simplest way to control the reflection coefficient presented to a device under test is by using a passive mechanical tuner. A mechanical tuner is made of an airline and a vertical probe, which is also called slug, which can move in the X and Y direction. Now, by changing the position of the probe, the magnitude and the phase of the reflected wave is changed, and so the gamma L can be controlled. Since the tuner is passive, the reflective wave A2 will always be smaller than B2 due to the losses in the tuner and in the measurement system itself. Therefore, the gamma L will always be smaller than 1. This is a quite severe limitation, especially for measuring high-powered devices where a small optimum impedance normally needs to be provided, so a high gamma, and especially for harmonic load pool, where typically a very high gamma is required for peak efficiency. For this reason, active load pool systems have been introduced now almost 50 years ago. In an active load pool system, the magnitude restrictions that are due to the losses in the system are overcome by amplifying the A2 wave through the use of amplifiers. In this case, the injected A2 wave can become equal or bigger than B2 so that the gamma L can reach and even exceed unity at the DUT reference plane. There's several advantages to an active system over traditional mechanical load pool, including gamma control, ease of integration, for example, on wafer. And also, since there are no mechanical moving parts and the system relies on electrical tuning, the tuning itself can be quite fast. There are two main architectures of active loads. In a closed loop system, basically an amplified replica of the signal B2 is attenuated, phase shifted, and then fed back into the device through the use of an amplifier. In this system, the value of gamma only depends on the gain and phase shift setting of the loop, independently from the input signal. For this reason, they can provide real-time the desired reflection coefficient, in theory, independently from the signal that's coming out of the DUT, so they can be extremely fast. On the other hand, the use of a closed feedback topology can cause loop oscillations when the forward gain of the feedback loop is bigger than unity. Another disadvantage of this technique is that in order to maintain the loop linearity, high power and very linear injection amplifiers are needed. In a open loop topology, which is the other alternative, a separate source is used to inject an A2 wave inside the device. The A2 wave is then adjusted in amplitude and in phase to achieve the desired gamma. The advantage is that this type of systems cannot oscillate as the loop is open. Obviously, the signal source, in order for this approach to work, needs to be phase locked to the input signal to the dot. One of the disadvantages of this technique is that it can be relatively slow because one needs to iterate in order to reach the desired and adjust the amplitude and phase in order to achieve the desired gamma. Now, both of these implementations in their most basic form are a traditional linear band. Dimensioning the amplifiers in an active load pool system is very important to achieve sufficient Smith chart coverage. In an active load, the injection power required to provide the given gamma L to the device under test can be calculated based on a Thevenin equivalent by using this equation, and it depends, other than on the target gamma, on the power output from the device under test, the output impedance of the device, and the system impedance. While the device output impedance and the target gamma are given, the power amplifier specifications and the system impedance can be changed in a system. Just to give an example, to achieve an output, a load impedance of 1 ohm, which corresponds roughly to a gamma L of 0.96, when the output power of my device under test is 200 watt, and the output impedance of a device is 2 ohm, I would require in a 50 ohm system more than 2 kilowatt of power. If I'm able somehow to reduce the system impedance to 10 ohm, the required power would only be 360 watt. Reducing the system impedance to 5 ohm would only require 142 watts. For this reason, pre-match test fixtures are used in high-power applications to reduce the 50 ohm system impedance to a lower value. Additionally, to reduce the power requirements on the load amplifier, passive and active tuners can be combined in what is called a hybrid active system. Here, the tuner is only used for pre-match, and these systems retain all of the advantage of an active load pool systems in terms of speed, coverage of the Smith chart, but at the expense of increased system cost and complexity. To conclude on this topic, here's an example of a measurement made on an LDMOS device up to 470 watt of power by using a hybrid active load pool setup. In this case, the injection amplifier used only had a peak power of about 200 watt. And even so, it was possible to completely close the max power and efficiency contours. So moving on to the next topic, load pool with complex modulated signal is gaining more and more importance in the validation and verification phase of wireless transceivers, where final power amplifier modules have to be tested for their linearity performance as a function of VSWR. And in fact, looking at the development of the telecom and Wi-Fi standards over the past decade, we can see, for example, from this table, how the used signal bandwidths are drastically increasing, going from 3G signals all the way down to Wi-Fi 6 or 5G signals. This in turns mean not only that we have to test more under wideband modulated conditions, but also that the requirements for the modulated load pool testing with complex communication signals are becoming more and more stringent. Now, looking at modulated load pool setups, the simplest way to perform load pool with complex communication signals is by using a system similar to the one described in the schematic here, where basically a vector signal generator is used to create the complex modulated signal. Passive mechanical tuners are used to provide the desired gamma or impedance both in the source and the load, and eventually at the harmonics. And vector signal analyzer or spectrum analyzer and power meter are used not only to measure the power of the modulated signal, but also quantities like linearity, such as ACPR or EVM. However, there's a problem with this type of systems, is that the reflection coefficient provided by a passive mechanical tuner basically is not constant across frequency and can vary quite significantly, especially in terms of phase. This is basically due to the physical distance between the slug itself, so the probe, and the device under test reference plane. Now, the longer this distance, the bigger the phase change will be. Typical values in conventional systems range basically from a couple of degrees per megahertz to 3-4 degrees per megahertz. And in this picture, you basically see what happens when you use a passive mechanical tuner to essentially provide an impedance across across the bandwidth of modulated signals. Basically, you see that going from 3G signals, which had 5 megahertz of bandwidth plus the ACPR channel, so 15, up to LTE signals, and now all the way to 5G, you see the phase rotation of the impedance provided on the Smith chart, which is essentially very unrealistic, and it's not what happens in a real circuits. And then for, especially with these newer signals, load pull measurements with traditional tuners under these conditions do not make a lot of sense. Now, specifically to resolve this problem and to enable wideband impedance control across the modulation bandwidth, the mixed signal vector load pull architecture was developed. In this topology, the gamma is controlled with an open loop active technique. The main difference being that the amplitude and phase of the signals are controlled by means of arbitrary waveform generators here and IQ up converters. So each one of these vector signal generators essentially constitutes an active tuner capable of providing of controlling arbitrarily an impedance across a modulation bandwidth. On the measurement side, the receiver architecture is very similar to that of the VNA, with basically an input coupler section, mixer for down conversion and analog to digital converters, and also an output section for measuring the B2 and the A2 wave, mixers for down conversion, and ADC. The main difference being that in these systems we use wideband analog to digital converters and basically no IF filters in order to capture wide portions of the signal spectrum. This architecture allows to measure wideband reflection coefficients, but also parameters such as ACPR and EVM. Currently, this architecture allows for wideband impedance control of up to 3 harmonics, both at the source and at the load, for a maximum modulation bandwidth of 1 GHz. And the current systems implementation range from a few hundred megahertz all the way up to 40 GHz. Now, in addition, with this system, ultra high speed CW and pulse CW load pull can be performed, and time domain RF voltage and current measurements, as well as behavioral model extraction. The technique used to achieve wideband impedance control is explained in these slides. Now, starting from our test signal, which in practical case is a periodic signal, very long periodic signal, but in a measurement system, this basically means that it's a very densely spaced multitone. If I excite my nonlinear device with this signal, I will see at the output an amplified replica of the signal, of course, along with all the intermodulation products, the harmonics, and the baseband products. But still, this will be a multitone. Now, since the reflection coefficient is described by this very simple equation that basically links the injected A wave to the transmitted B wave, essentially, if I can measure my B2 wave at all of those frequency tones, and if I can create an A2 wave at all those frequency tones, and I can control it arbitrarily in amplitude and phase, I can essentially provide an arbitrary reflection coefficient across the bandwidth by using this simple relation. In reality, what we do is not measure the A2 and B2 wave in the absolute sense, but rather measure the gamma versus frequency, compare it to our target gamma, and use software iterations to adjust the A2 wave at all of those frequency components in a loop to achieve an arbitrary reflection coefficient versus frequency. An example of application of wideband impedance control is shown in this example, where we measured the 10-watt LDMOS device in package. From the CW data, we basically gather the optimum load at fundamental and at second harmonic for maximum power added efficiency. Afterwards, we perform this test with 3-carrier wideband CDMA signal. And in a first example, we basically provided a constant reflection coefficient versus frequency across the full bandwidth of the signal. In the measured results here, you can see how, in this case, the measured spectrum is quite flat across frequency. There's some spectral regrowth, of course, but quite interesting, the average PA is about 38% at 33 dBm of output power. In a second case, we tried to emulate what happens with a conventional load pull system, assuming a gamma variation of 40 degrees per megahertz, which represents basically the variation given by a 70 centimeter cable. So this is what would happen in that case on the Smith chart across the bandwidth of the signal. You see for the fundamental load impedance, quite a big phase variation, and at the second harmonic load impedance, an even bigger variation. In this case, which is quite extreme, you see very severe in-band fluctuations and very pronounced asymmetry out of band. In terms of efficiency, also the decrease in average PA is quite drastic, and it's down to 20% at 31.5 dBm of output power. It's important to stress that this is only the effect of the gamma variation versus frequency given by the passive impedance, which basically is an artifact of the measurement and is not what happens in a real circuit. In another step, what we try to do is to emulate what would happen in a real circuit, where you basically have a matching network designed and placed very close to the transistor. So we implemented 2 different matching networks using a circuit simulator. In a first implementation, you see just a simple stub to implement the harmonic matching here. And in this plot, you see the corresponding fundamental and second harmonic reflection coefficient as a function of frequency. In a second example, we implemented the harmonic matching with a radial stub. And in this case, you see a bigger phase rotation at the fundamental frequency and a smaller phase rotation on the second harmonic frequency. In the 2 cases, you see the efficiency and output power is quite close to the case with no phase skew, with no phase distortion. You do notice that in the case of a conventional stub, the power added efficiency is 38%, as high as the ideal case. Whereas with the radial stub, you would lose about 2% average efficiency, just due to the matching network implementation. So moving on to a slightly different topic, I would like to discuss how to measure error vector magnitude or EVM in combination with active load pull. So to give some background, Error vector magnitude is a metric that is used to quantify the distortion introduced by a system when excited with a modulated signal. So in case of a high-frequency system, the distortion contains contribution to noise, frequency response, and nonlinearity. So if we refer to the picture here, where you can see the ideal constellation of a complex modulated signal, if you excite a nonlinear system with such a signal Tx, the output signal Rx would be distorted due to both a distortion piece, which is somehow correlated with the input signal, and a nonlinear distortion, which is uncorrelated with the input signal. If you want to express this in math, the signal Rx is given by this equation. So as the product of the input signal Tx and the transfer function of the channel H plus D, which is the distortion. Now the error vector magnitude quantifies that part of the distortion, D, which is not correlated with the input modulated signal. The process of removing the correlated piece of the distortion is called equalization. So after applying an equalization to our signal Rx, we would get back the signal Y without the correlated distortion, and the error vector magnitude, the EVM, measures the distortion as the difference, the vector difference in the constellation between the input signal and the equalized output signal, as shown in this equation here. So traditionally, EVM is measured as the difference of the symbols in the constellation diagram, which means you need to be able to demodulate the waveform acquired and extract the constellation. And this is what is typically done when using a vector signal analyzer. However, in the case the signal is not fully known, the EVM measurement can also be generalized by calculating the difference between the ideal and the equalized output signal waveform. So without the demodulation, but fully the time domain waveform acquired from the signal. So based on this, the EVM can be calculated both in the time and in the frequency domain. And you see that the signals can be expressed here both in the frequency domain as in the time domain. And what we can do is we can calculate it by reconstructing the signals that are acquired with our instrument to the time domain, and by applying the following equation in the time domain. So the EVM is the difference between the equalized time domain signal and the ideal signal normalized to the amplitude of the input signal. If we expand this formula and you extract Y from this equation here, you see that all you need to do is, so if you have measured the signal Rx, is equalized by calculating the inverse of the channel transfer function to calculate the EVM. And in other words, you need to apply an equalizer to the received signal in order to remove the channel transfer function from the measured signal. In our case, this is done by estimating a filter, by using a FIR filter, as shown in the references that are here below. So on the mixed signal load pool system, we use this generalized method for EVM measurements, which gives us the flexibility to essentially operate with any modulated signal. A nice advantage of using this method is that thanks to the possibility to average significantly, we can achieve very low noise floor, as is shown in this slide, where the EVM is measured at different frequencies and for different wireless LAN 6 signals on a through. In these measurements, an average factor of 100 is measured. What is interesting to note is that at very low power, the measurement is essentially dominated by noise. At some point in the power sweep, there is a sweet spot where basically the measurement is optimal. And then at the end, the receiver nonlinearity kicks in. So essentially, in order to achieve a very low noise floor across a wide range of input power, the receiver attenuation must be changed within a measurement. Another example of an EVM measurement in correlation with load pool is shown in this slide, where again we used a wireless LAN 6 signal with 80 megahertz of bandwidth to measure an actual amplifier across the load. So you see that you can achieve quite a low noise floor, and then at some point the device distortion kicks in. Another extremely important requirement for proper linearity characterization of a nonlinear device is to be able to control the termination that the device sees at low frequency. In fact, the transistor linearity strongly depends on what happens at the baseband frequencies and at the harmonic frequencies. And this is because in a nonlinear device, as it is shown in this figure, there are two kinds of third-order mixing products. The direct product, which is this one, and comes from the mixing of the fundamental products, like 2F2 minus F1 and 2F1 minus F2. And the indirect products that results from the mixing of the fundamental frequencies and the baseband and the second harmonic frequencies. So F1, F2 with F2 minus F1 and 2F1, 2F2 and F1 plus F2. These two different products, they can sum up or cancel depending on the termination seen by the transistor at both baseband and second harmonic. For this reason, in order to properly characterize the linearity of a transistor, one needs to take very good care of what happens at not only at the harmonics, but also at the baseband impedance. And this can be done, for example, for a transistor in package by using a proper test fixture with proper biasing integrated on board, or as we're trying to do on wafer characterization, we need to be able to control the baseband impedance by using either a passive low frequency impedance board or active baseband impedance source and load pool. So in this schematic, you see an example of how in a mixed signal active load pool system, we can control the baseband impedance also actively. The technique is essentially the same as for the high frequency load pool, except that in this case there is no up conversion. So we're able to measure the baseband impedance by using a combination of low frequency couplers and current and voltage probe, and this allows us to measure the baseband impedance at input and output from all the way from DC to a few hundred megahertz. And there is an active load which is composed by a direct arbitrary waveform generators fed to a DC-DC converter. In this particular measurement, one of the most critical pieces is this baseband modulator, which is essentially the same component that you would use in an envelope tracking amplifier or similar. But for high power baseband characterization, we had to develop this on our own. And this is an explanation of how we did it. Where we basically used a diplexer to combine very high power, high current and voltage DC-DC converter and a low frequency but high power RF amplifier. So the combination of these two makes for a very high power, high current and voltage DC-DC converter, capable of providing 50 volt of DC voltage with a maximum of 3 amp of current and a maximum RF output power of about 44 dBm. And here is an example of what happens if you don't provide the proper baseband termination to your transistor during the measurement. In this example, we use an LTE signal on an LDMOS device. And here, after the optimization of the fundamental and harmonic terminations, we look at what happens if you don't provide the proper baseband impedance termination. So the curve in blue is the result of an ACPR measurement and a spectral measurement in this other plot, when the baseband impedance is just left passive. So there's a direct connection to the DC supply from the biased ion wafer. The curve in red shows what happens when you actually apply a baseband short. So you see there's the best linearity in this case. And the curve in green shows what happens when we emulate a 150 nanohenry inductance on the bias line. So, and finally, an example of a bit of a more advanced application for this type of baseband impedance control measurement could be the linearity optimization of bipolar transistors on wafer. And this is the work done by my former colleague Koen Baseband. We're basically using a mixed signal harmonic load pull system. He was able to control the baseband and the second harmonic impedance and optimize them in order to find the optimum linearity locus as a function of output power and collector quiescent current. So to conclude this presentation, I have shown an overview of active load pull techniques. I've discussed modulated load pull measurements and system. And I gave some additional requirements for doing meaningful linearity characterization of transistors. With this, I would like to thank you for your attention, and I'm looking forward to the question session. Thanks.